We're on lesson 3 of chapter 9, which is linear functions. First, we're going to identify linear functions. Then we'll write an equation for a linear function. Then we'll solve a real-world problem. First, a linear function. That's a function that can be described by a linear equation. For example, the ones we're working with last chapter, such as y equals mx plus b, that's a linear function. You have your input, which is x, and you have your output, which is y. So when x is 1, you get a different answer for y. When x is 2, you get a different output for y. We're going to be learning about function notation, though, today. And that's one way to write a linear function, where x represents the input value and y represents the output value. So this is one way of writing it here. We have our output value on the left, f of x equals the x plus 4. So if we use an example for that, when x is 1, we would put 1 for the input value, which would be 1 plus 4, which equals 5. Let's try a couple examples. First, we're going to identify whether functions are linear. So it says determine whether each function is linear. If so, give the slope and y-intercept of the function's graph. For this one, we're not quite complete yet. It looks like we have to do some distributive property. So we have to distribute this 5 to the x and the 2. So if we rewrite this, we'd have f of x equaling 5 times x, which is 5x, plus 5 times 2, which is 10. So is this linear? Well, this would be linear because it's written in the form of mx plus b, or the slope times the x plus the intercept, and we know that that's a linear equation. So the slope in this case would be 5, so m would equal 5, and the y-intercept would equal 10, so b would equal 10. Now we have f of x equaling x squared plus 1. And as you're going to find out, this can't be a linear function. Whenever you have the variable with an exponent, that's going to make it very much nonlinear. Because 0 squared is 0, 1 squared is 1, 2 squared is 4, 4 squared is 16. Notice what kind of pattern that takes? It's very much a curved pattern. So we'll say nonlinear. Now we actually have to write an equation for each linear function, or a rule they'll call it, which is the same thing. So we want to write this out in slope-intercept form. So f of x equals the slope times x plus b. So first we could find out the intercept, then we could figure out the slope. When x is 0, what is y? Well, that's negative 3. So that's the b here. Now what's the slope? You can do rise over run, so we rise 1 and we run 1. So 1 over 1 equals 1 for our slope. So if we write this out, it would be f of x equals 1 for the slope times x minus 3, or just x minus 3. You could always test out your answer too by plugging in the x value. So let's say when x is 2, 2 times 1 is 2, minus 3 is negative 1, right where that y is. Here we're given a table, and we're not given the value when x is 0, so the y-intercept won't be that easy to find. But we can find the slope. Remember, the slope is rise over run. So we could choose two different points in the graph. We can say 2 and negative 4 and 1 and negative 7. So the rise, we went from negative 7 to negative 4. That's an increase of 3. The run was an increase of 1. So therefore the slope would equal 3. Now we can figure out the y-intercept by plugging in any of these points to solve it with that slope. So we could say y equals mx plus b. Plug in negative 13 for y, equaling our slope, which is 3, times what goes to the negative 13? That's negative 1, plus b. So negative 13 equals 3 times negative 1 is negative 3 plus b. Add 3 to both sides. And then these would cancel out, leaving us with b equals negative 10. So now we can write our function. Here's our slope, here's our y-intercept. Let's write that out. f of x equals the slope, which is 3, times x, plus the y-intercept, plus negative 10, or just minus 10. Now we can solve a real-world problem. It says at the beginning of a voyage, the Queen Elizabeth II's fuel tanks contain about 1 million gallons of fuel. At cruising speed, this fuel is used at a rate of about 3,500 gallons per hour. Find a rule for the linear function that describes the amount of fuel remaining in the ship's tanks. Then use it to estimate how much fuel is left after 10 days. Well, first we need to figure out the y-intercept and we need to figure out the slope. We can write our equation out here, y equals mx plus b. Well, b is the y-intercept when x equals 0. So if it's 3,500 gallons per hour, we would find how many gallons are left when the hours are 0. So before the trip has started. Well, the fuel tanks would have 1 million gallons of fuel before going. So that would be our y-intercept, so plus 1 million. That's a positive 1 million. Here we see this fuel is used at a rate of about 3,500 gallons per hour. So the fuel tanks are not going to be increasing during the trip, they're actually going to be declining by that rate, meaning that the slope's going to be negative 3,500. So we have negative 3,500x plus 1 million. So we can make this part our function, so the function of our input equals negative 3,500 times our input in hours plus the 1 million. So when it's 1 hour, you would plug in 1 here, so negative 3,500 times 1 plus a million. If it's 10, you would plug in 10 here. We need to estimate how much fuel is left after 10 days. Since this is hours, I'd have to multiply the 10 times 24. Well, 10 times 24 equals 240. So my input's going to be 240 hours. So the function of 240 equals negative 3,500 times 240 plus 1 million. If we're going to multiply this out, this gives us negative 840,000 plus 1 million, which means we did not run out of gas because this is not quite as much as 1 million. So negative 840,000 plus 1 million is positive 160,000. Running a little bit low on gas. So the function of 240 equals 160,000. So there'd be 160,000 gallons of fuel at 240 hours or 10 days.